whole face. Okay. So from yesterday, one thing I wanted to clarify is the idea of something called standard position. In your homework, this phrase is used quite a bit. What it means is what we practiced yesterday. What we discussed yesterday was that in order to draw an angle, we wanted to always draw it the same basic way, with an initial side going straight to the right at the 0 degree marking, and then your terminal side going where you want the angle to end up. There's one last component to make this drawn correctly. It is the arrow to showcase which direction you're going in. Example over here. This is an angle of 300 degrees in standard position. I can tell it's 300 degrees because A, of where it's located, and B, because of how I've drawn my line. You see this little red marking, this little arrow marking indicates that I'm going counterclockwise, so I'm counting in the positive direction, and I'm stopping at 300. So in this picture right here, this is a 300 degree angle drawn in standard position. The requirements: starts on the 0, ends at 300, indicates with the arrow which direction it's going to indicate that it is positive. If I need to go past 360, this arrow is really important because it tells you how many times I'm going past in the picture. If I wanted to go to, say, 480 degrees, what I do is I start at 0, wrap around to 360, and then continue until I get to 480 degrees. But that arrow is the indication that I'm supposed to go either farther or closer to my initial starting place. To go for negative, which is over here, I have drawn in this picture negative 80 degrees. Drawn in standard position. Again, the initial side is the same. It's always on the 0. Notice that my line, my terminal side, is going in a similar location to 300. I can tell it's negative because of the arrow. The arrow indicates that I'm going clockwise, which in this case is negative. So I can see here, this arrow going clockwise indicates that I'm supposed to be looking at the negative version. Because remember, this 300 is coterminal to a lot of other possible answers. It's coterminal to 660 degrees. Just remember, 360 degrees past it. It's also coterminal to negative 60 degrees. So the arrow indicates which one of those I'm supposed to be looking at. Am I supposed to be looking at negative 60, at 300, or at 660? But again, drawing it in standard position is, again, the bar going across 0 indicating the starting place, the terminal side indicating where it's going to finish, and then the arrow to indicate how many times I'm looping around. So this is 300, this is negative 80. So if a problem mentions wanting to do something in standard position, copying a picture similar to this is what you're supposed to do. Again, the arrow indicates how big it is supposed to be and makes sure to tell you whether it's positive or negative, whether it's the first number or one of the many possible coterminals of that number. Because again, this negative 80, if I put the arrow in a different place, it could be one full turn past it at, say, negative 540, or sorry, negative 440. Or it could be going in the other direction and be at positive 280 degrees. Because they're in the same location in terms of the picture. The arrow indicates which direction I'm going in and how far I'm going in that direction. Because again, this could be drawn in negative 80. If I drew it instead like this, the green one is not negative 80. The green one is actually negative 440. Because it indicates that I've gone past once, going to negative 360, and gone around to negative 80 a second time. I like to think of it like the locker combination you have whenever you go to undo your locker. Like if you turn one full turn, it's 360 degrees. If you turn the other direction, it'd be negative 360. If you're supposed to go past that, the numbers keep racking up. But how to indicate that is you go all the way around once with the arrow, and then keep going with the arrow to indicate you're going to the next value. If you gotta make 2 turns, swoop twice. Turn into a little corkscrew. If you're not careful, this can start to look like hypnosis, though, so be on your guard. If you find yourself being dazed by your homework, it might not just be the math. So, this is standard position. Now, this is the first primary term we need to talk about. The second term we want to talk about today is an idea that's also in your homework referred to as subtended. This idea is not seen in geometry because, again, geometry is strictly based upon the shapes, so triangles, rectangles, kites, squares, rhombuses, pentagons, hexagons, those things. Whereas in trig, we can go past 360 degrees, so we don't rely upon shapes as much. Subtended is a concept that should be taught in geometry, but I'll be honest, I taught geometry, we never discussed it because it's not required to do it. It's a specific kind of way of drawing the angle, and in fact, everything we've done so far has been subtended. So let's go to a definition. There are practice problems. Let me have it. It's very tiny. Very tiny. Okay. Definition. Subtended. This is usually in reference to a specific angle. So an angle that is subtended. The definition of a subtended angle is an angle that is drawn in the center of a shape. So in geometry, you talked about angles that were drawn along the edges of the shape, right? You talked about having a right triangle being a triangle that had an angle in one of the three corners. You talked about a square as having, angles in each of its corners. A subtended angle is one which the center of the shape creates the angle. Every angle we've drawn so far in standard position is also subtended. So a standard subtended angle is just an angle drawn in the center of a circle. Now this would be subtended but not in standard position. So in this picture, this blue angle right here, this is subtended but not standard.
It's drawn inside of it.
It's drawn inside, specifically in reference to the center. So if I'm going to put my definition, I would say is an angle that rests inside. Now, it is most common to do it with circles, but you can actually do it with many other shapes. We'll only talk about the circle version, but in geometry, you can talk about more advanced ones of these, where you draw inside of triangles or inside of rectangles. We're just going to focus on the circle one because it matches to our unit circle. So it's an angle inside the shape, whose vertex is the center. We discussed last time how the vertex is where the two rays come together to create our angle. And so that vertex is at the center of the circle. Now, this blue one is subtended, but not standard, as would be this red one. This red one is also subtended, but not standard. So every angle in your homework, if you draw it the way we discussed in standard position, will by definition be subtended. There are many homework problems that describe a situation where it says, hey, it's a circle with a 110-degree subtended angle. And if that's the case, that just means it's a circle with a center angle of 110. That's all it means. I would recommend for your homework, if a problem asks you to draw a picture about a subtended, draw it in standard position to practice standard position. Because everything we're going to do is going to be in standard. So I would suggest keeping it that way when a homework problem mentions it. But again, subtended angles are angles that exist inside a shape, specifically where the vertex is also the center of the shape. If you want to see an example of this in another shape, like I said, we won't do this in this class, but if you want to see an example, if we were to take something like a square, or something pretty close to a square, I hope, subtended angles would be ones that are at the center. So this would be our subtended angle. So if you've seen weird, funky looking analog clocks, all those sides of those clocks create subtended angles. That's all they do. They just create angles at the center of some shape. And again, in geometry, we tend to focus upon, oh, this angle's 90 degrees and this angle's 90 degrees. But in Trig, we're often associating to something more advanced, where it's like, no, we're looking at the general structure of it, saying what it can do. Those are our two main definitions to prep us for the homework assignment. We've already seen how to draw an angle. We've talked about the pieces of an angle, things like the vertex, the initial side, which is always at 0, the terminal side, which is where it ends up. We've talked about now what subtended means, which is to draw it inside of a shape located at the center. And we've talked about what standard position is and how that's different from what it is in geometry. Now, to finish with today, we have 4 basic formulas that are required to do the last few problems of your homework. The last few problems of your homework are applications, your first real applications of trigonometry. So a lot of trigonometry is used specifically when it comes to physics. And so you'll see the last couple of problems are all physics questions. And in fact, all of your formulas are physics formulas. Here are the four you need. You notice that in black I have listed what the formula itself is, and in red next to it I have tried to describe what each piece is in case you don't know. So here, the first one, arc length. If a question asks anything about the arc length of a particular circle, the formula we're going to use is S equals theta times R. S is for arc length. Somebody asked last block, why S? My answer, don't know. You can't use A because A stands for area. You can't use L because L stands for length. And you don't want to confuse length with arc length because they're different things. So S, I guess, is just an unused letter. I don't know. So arc length. If you want to determine the arc length, it's this formula. S equals theta times R. Remember, theta is one of our Greek letters from last time? So in other words, the arc length is equal to the angle times the radius. And because of how we learned about algebra, you can use this in multiple ways. You can plug in theta and R to find the arc length. You can plug in the arc length and theta to find R. You could plug in R and the arc length and find theta. You can work all kinds of ways. But one important note that I should point out about these formulas work best in radians. In radians. You want your angles in radians, these formulas to work. Some of your problems already have them in radians. Some have them in degrees. And so don't forget your formula to convert the two. You can either use pi over 180 to convert from a degree to a radian, or 180 over pi to convert back. But again, these formulas work best if it's in a radian. So you may have to make an adjustment before you start using the formula. Keep that in mind. That's the first formula. S is equal to theta times R. Now, this is arc length. In a picture, arc length is defined as, let's go back to geometry here. We have theta, we have R. So in a picture of my beautiful, beautiful circle, thank you very much. In a picture of my beautiful circle, the arc length, S, is right here. This distance is S. It's the length along the arc. How do you wait? So again, the arc length is defined as the length of the arc, the length of the piece of the circle. So if you remember your geometry, this refers to things like the circumference. In fact, if you think about this formula, if you wanted the total length, well, that would be 360 degrees or 2 pi. So to find the arc length, you would use 2 pi r, which is the formula for circumference. Yes. The second one is the area of a sector. A stands for area. So area is equal to 1/2 theta r squared. So 1/2 times theta times r squared. Remember, theta represents the angle. R represents the radius. So again, in this picture, in blue, this is the arc length. Now in yellow, that is the area. Classic awkward examples to help remember these ones that are different. You can do things like S stands for your speedway, the distance around the track, whereas A stands for the area of the pizza, how much pizza you eat. Okay. So we have arc length, which is the distance around the edge. So this is your crust of the pizza. You have the area of the sector, that is the total length of the entire thing, the big piece. So if you're in blue, arc length. Up here in yellow, the sector, area. Now, those two are both discussed at least partially in geometry. These last two are not talked about at all in geometry, which is a shame. They're talked about in physics. So let me make one more picture here. A picture that I promise will be just as good as the previous ones. Here we go. These last two are pure physics applications. So when you look at your homework, you'll see that some problems sound like geometry problems. They're using these two formulas. They're asking about areas, they're asking about perimeters, they're asking about distances, they're asking about size. Those are arc length and sector. There are other problems that sound more like a physics class, where they have physics applications to them. Because Trig was really helpful in designing how physics works. And if you ever take a real physics class, a lot of the formulas that are used in physics involve trig. You'll see cosines in them, you'll see sines in them, you'll see tangents or other trig functions in them. So, the last two are pure physics applications, but I want to explain what they are first, because they're very subtly different. And it helps if you've ever driven a car when I explain these two. Here we go. My picture. Beautiful circle, Douglas. Thank you. I know. There's Mr. Douglas in his beautiful car, driving around a nice circular track. I'm trying to NASCAR. You know. I think I can do it. I'm pretty sure Dale Earnhardt Jr. He's afraid.
That'd be an oval.
Yeah, I can't draw an oval. I can't draw an oval any better than I could draw a circle.
That's a car.
Yeah, totally, definitely. That's very much a car. Okay, so here's where it's going to get real technical here. If you've ever driven around a corner, like there's a lot of backcountry roads around here, you guys know what I'm talking about. If you drive it too fast, you might notice a certain phenomenon happens. You feel the pressure of your turn pulling you into the corner, even though you're driving into the turn. Now in physics, they call this momentum or inertia, right? As you turn that right-hand turn, your body gets pressed to the left. Because what's happening is as you're turning, a piece of your motion is still trying to go forward. This piece of the motion is referred to as the linear speed, because it's the speed that's trying to go in a line. This is different than the speed of the turn itself. If you actually look at your speedometer keeps track of your angular speed, the speed along the curve itself. It does not keep track of the linear speed. So you look like you have your hand raised. Okay. So in this picture, the linear speed that you are traveling looks like this. And in physics, it's represented by the omega symbol. It's that pressure you feel of the car trying to go forward and you forcing it to take the turn. It's a linear speed because line stands linear. Linear means straight. So it's that feeling of trying to go forward. As you're making the curve, this is your angular speed, which in this case we use with v, which stands for velocity. Now, in most cases, we care more about the actual speed, the velocity, than we do about the linear speed. But cool things start to happen when you start to change these two. And if you've driven before, you might have noticed it. If you try to take the turn a little sharper, pull a little more, there's a reaction to your feeling as you go the other direction. You feel pressed harder because the difference between the two gets bigger. One of them is changing and the other one is reacting to it. So these two, as it turns out, are related to each other. As you push this one harder by either changing the angle or shortening the amount of time, you change your angular speed as well, and vice versa. They always have this effect, where if you change one, the other has to react to it. So again, the linear speed is that straightforward feeling as you're driving in the turn, that feeling that tries to keep you going straight down the road, even though the road's turning. You fighting that and turning your wheel, that's the angular speed. It's trying to match to you. It's trying to follow the road itself. And they are different values. Oftentimes, your linear speed tends to be lower, but not always. It just has to do with the physics behind it. So here are the formulas. We use omega for linear speed, because you can't use s, because it's already taken. You can't use L, because that's length. linear speed's omega. Go with it. Is equal to theta over t. So the angle you're traveling at divided by time.
That's a loopy W?
Yep.
Oh, I did.
That's omega.
It didn't have the loop in it. I wrote it as regular old W.
Yeah, see, that would make it very, very
So cool.
hard.
It's actually
Better?
yeah. That's the ugliest symbol I've ever seen.
Okay.
Not necessarily
So-
yours. I mean, mine looks bad too. It's the symbol in itself.
I'm not perfect. All right. So again, we got a translation next to it. If it asks for the linear speed, this is a simple formula for it. It is theta over t. So you need to have the angle that you're traveling with divided by the time you're traveling along it. So again, notice that both these have to deal with the angle, just one does it directly, the other does it by pulling from another formula. S, we've already seen, is the arc length. Okay? In this case, the velocity is equal to the arc length divided by the time. So how far you're traveling divided by the time. These two are related to each other. There's actually a formula that connects these two together. It's a really neat little formula. You won't see it in many textbooks because, well, they're not that big a deal on this. The formula looks like this. V is equal to omega times r. And if you plug in all the pieces, it works out very nicely. But this means that your angular speed, the speed around your turn, has a direct relationship to your linear speed, how far you feel like you're being pressed forward. It's a multiple of it. So, questions about our four formulas? Make sure you have all four down. Make sure you know what they mean. Don't just write the formulas down. Don't just write the symbols. Tell what they mean, because it makes no use if you have a formula that you don't know what it does. Okay? And make sure you know our two terms we talked about today, standard position, which is an extension of last time, as well as subtended, which is a specific way of drawing the angle, which is related to standard position. Okay, any other questions? Okay, tomorrow we're going to do some examples together in class. The idea is to get some of the homework problems out of the way, especially those first couple, which are the ones that ask for the concept, whereas the rest are more about the physically doing of it. Many people have an easy time with the doing it, but struggle to talk about it. So we'll look at some of the problems tomorrow. Remember, the homework assignment is due on Friday in class. We'll spend some time in class answering any last-minute questions, but the rest we will start presenting and prepping for next week. Which again, remember, November is going to be a lot of this kind of geometry topics. It's hard. I hope so. All right.